Hello everyone. The last time we met, we were discussing the second assignment, in particular the design of the transimpedance amplifier. We looked at the transfer function of the transimpedance amplifier and we worked out certain trade-offs. The objective is to design the transimpedance amplifier with a certain gain RF, but because of the finite unity gain frequency of the amplifier, it turns out you cannot increase RF indefinitely. If you try to increase the gain, you will end up with a large value of the feedback resistance, which gives you a pole in the feedback path, which makes the circuit unstable, or at least tend towards instability. Okay, so this rings a lot and it's not very useful. So we saw a couple of methods of overcoming this. The first one was, of course, to make RF small enough so that this doesn't happen. Second thing is to try and introduce a zero in the path so that when the loop gain crosses unity, the slope is 20 dB per decade. Okay. The last thing that we were discussing was to do something like this. We introduce a resistance from the inverting input to ground. Okay. The idea here is to reduce the loop gain. Okay. So if you have loop gain of this sort, it will be unstable. So you push it down by some amount, it will become stable. Okay. So we saw that if the pole is at 40 megahertz, then we have to push it down below unity. So we have to push it. We can only make a bandwidth of 28 megahertz. Okay. But there are a couple of things that happen. One is, of course, the reduction in loop gain. The other thing is the pole value itself is influenced by Rx. Okay. So this picture that I drew is not quite accurate. When you introduce Rx, what happens is the picture goes from being this to the gain becomes smaller, but also the pole goes to a higher frequency. Okay. So you don't have to reduce it by as much. So if you do something like this, the pole would have gone to a higher frequency and then it drops off. So both the loop gain reduces and the pole moves to higher frequencies. So the reduction in bandwidth is not as much as this. Okay. So we can work out what it is. Okay. Okay, the voltage at the output, if it is a V naught, at the input it is V naught S by omega U. So I is so this part is the current flowing here and here. Okay, plus the current flowing through RF. Okay, so V naught by I turns out to be so again we get a second order denominator which we can adjust for maximal flatness. This is divided by omega U. Okay. So let's say we adjust for maximal flatness. What's the bandwidth we'll get? This is 1 over omega n square. If you adjust it to 1 over square root of 2 quality factor, the bandwidth is omega n. So the closed loop bandwidth Okay. So I will leave it to you to work out the conditions to get maximal flatness. So basically you have to adjust Rx so that you get a quality factor of 1 over square root of 2. Okay. So what was the closed loop bandwidth we got when we had introduced the 0? Yeah, for this. So this actually gives you a better bandwidth compared to introducing the 0. Okay. So what might be the disadvantage of this? We haven't discussed it, but it turns out that this circuit is noisier. Okay. The signal to noise ratio you get from that circuit will be poorer compared to what you get from this one. Okay. That's the disadvantage of that circuit. And there was another suggestion. So here you introduce a resistance between the photodiode, between the diode and the op amp. Okay. The idea is still the same. Before, if the capacitance was here, okay, so the phase shift at high frequencies of the feedback network was minus 90 degrees. Okay. So before the circuit looked like this, right? So the phase shift from here, V out, to the op amp input is minus 90 degrees. What is it in this case? What is the phase shift here? 0, because this becomes a short and you just have a resistive divider. Okay. The action is similar to that of, so we had this and we added a capacitor. Okay. Now what is the phase shift at very high frequencies between this and this point? 0, because it becomes a capacitive divider. In this case it becomes a resistive divider. So the idea is the same. Okay. The resulting transfer function will have a 0 and a pole, and you cannot make it maximally flat. Okay. But that's okay. So let's for now assume that that part is fine. So you can calculate this whole thing and you get V naught by I to be RF times 1 plus S CD RX, I think, divided by some D of S. And it turns out also, I mean, you can make such a function maximally flat, but in this particular case you cannot. The values are such that you just cannot get it flat. It will always give you a peaking in the frequency response. Okay. But that's okay. Maybe you can adjust the peaking to some small value, let's say 0.5 dB or something. And you also get some high bandwidth because of this, at least higher than if you didn't use it. I mean, if you didn't use it, you would have peaking, so it was not useful anyhow. So do you see any shortcomings in this circuit? What practical problem might there be if you use this? Noise? Probably not. I haven't calculated it, but I don't think so. So yeah, one possibility is that it helps in stability, but the bandwidth may not be as much as others. So I have to work it out. I forgot what the bandwidth is. Have you built inverting amplifiers or photodiode amplifiers, any of you, on a PCB? Nobody? Okay, so let's then proceed theoretically. So first of all, the circuit I gave was this, right? What he is suggesting is that the reverse bias on the diode changes because of the resistor. Let's look at it and decide whether it's a problem. Okay. So which way will the current be in this? Because of the photodiode, which way will the current flow? This way, right? It flows against the normal bias of the device. So what happens? So let's say this is at 0 volts. This is at 0. You are saying this will be at some negative voltage. Is that's the, so first of all the diode must be reverse bias. So this may be okay. Huh? Oh sorry, it will become forward bias, then you will have to, then you will have to change the bias of this point. Okay. So that may be okay. Okay. So basically see, the bottom side is not really connected to 0 volts, right? Because then you have, even in this case, even without the resistor, it's not connected to 0. It has to be reverse biased with a certain voltage. That's how the photodiode works. Okay. So maybe what you will do is, you will put the bias voltage here, and for signals, you ground it. Which one? No, I mean, but I can use a different value of V bias here, right? No, for the largest current I expect, I can adjust the V bias. So that is not a severe problem. Yeah, you have to be aware of it, but it's not a severe problem. Okay. So what is this capacitance? Why did we put it there? So it's a diode capacitance. But can there be any other capacitance there? The input capacitance of the op amp. Because in this, I simplified the whole thing and said you call it diode capacitance. I mean, this can be anything. The op amp will also have a capacitance. Okay. And of course, any tracks on the PCB, that will also have a capacitance. Okay. So all of it can be lumped into that CD. So in our analysis, we have to plug in a different value, not just the photodiode's capacitance value. So in light of this, what's the difference between, let's say, this circuit and this way of introducing the 0? Here, the op amp capacitance appears at this point. Okay. So in the other circuits that we saw, op amp capacitor appears with CD, so it modifies the value of CD. So that means that it will affect our bandwidth in some way, but it will not affect the stability. But what happens here? We have capacitance, another capacitance, so what happens to stability? Order increases, but that's okay. Can you just look at it and say whether the stability gets worse or better? What is the phase shift of this network from the output to the input? Let's forget the op amp at high frequencies. V out to the input of the op amp. What is the phase shift? It is minus 90, right? Isn't it? So this probably won't affect the phase at all, but this is going into a capacitor. At high frequencies, all of the current will go into the capacitor. Okay. So the phase shift around the feedback is 90 degrees again. It's exactly like if you didn't have any of this. Okay. Of course, the frequencies over which it happens may have been modified, but at high frequencies you get 90 degrees phase shift. So this means that the stability of this is also not very good. Okay. Only if you don't have this capacitance will the 0 help you. Okay. If you have this capacitance, you have an additional pole which will take the phase shift back to 90 degrees at high frequencies. Let's take this network. I will draw it the same way. So this resistance was put in to introduce a 0. Okay. What happens when Rx is very small? Let's say nearly 0. What do you think of the stability, or what do you think of the phase shift of the feedback? Huh? What is the phase shift in the feedback? Minus 90 degrees. Okay. When Rx is very large, what happens? So you can ignore this part and it will still be a low pass filter. So in general, this tends to give you a lot more phase shift than the other circuits we saw. Okay. But if you do have this, you will have a capacitive path, capacitive divider. Okay. So this will have very little phase shift at high frequencies. You can go and work it out and see, but because you have a capacitor here, you will get additional phase shift. So it's not as effective a way of stabilizing the circuit as the others. So we saw several ways of stabilizing this. So basically, see this circuit, some of you at least may come across this, is to make this using discrete op amps. Okay, especially if you go into photonics and so on, you will get exactly the same circuit. You will have a photodiode and you will have to convert the photodiode current into a voltage and then do further processing. And as usual, the goals will be to do it with as little noise addition as possible, okay, and get as much gain as possible. The two are somewhat related, and also to get as much bandwidth as possible. That may be another criteria. So this is quite an important circuit in that area, as well as it's representative of another circuit which is used even more widely perhaps. So this is an inverting voltage amplifier. So what happens? You will have a parasitic capacitance from this. What do you think the effect of this is going to be? So let's say I design it for this particular bandwidth. So will I see something like this? This is strange. I thought we discussed all of this in the last class. So I have this circuit, okay, and with a certain op amp characteristic, it gives me this thing. What happens if there is a capacitor? When you put 4 kilo ohm as the transimpedance, what was the result? So what will happen if you have a capacitance here? So let's say this is driven from an ideal voltage source. This is Ri, this is Rf. Let's say the op amp is an ideal integrator. What will be the loop gain without any extra capacitance? So it is omega U by S, Ri by Ri plus Rf. So what will the loop gain plot look like? It will get shifted. Okay, it's just a scaled version. So if this is omega U, this will be omega U times Ri by Ri plus Rf. Now I put a capacitor here. What happens? This is the circuit we have, which gives you Ri by Ri plus Rf. If you also have this, you will get so after you get used to, after you do a lot of analysis, this kind of thing you should be able to tell straight away. Okay, you can't be doing analysis for like circuit with 1 or 2 resistors and capacitor. The impedance of this parallel combination is Ri by 1 plus SCP Ri. I am not suggesting that you go and memorize this. I am just saying that after you do enough analysis, you should be intuitively comfortable to write it down. Okay, and this will give you Ri by Ri plus Rf, 1 by 1 plus SCP Ri parallel Rf. Okay. So the DC gain is Ri by Ri plus Rf. That's clear. It's a resistive divider. And the pole is, with the input disabled, you see Ri parallel Rf across Cp. Okay. So the pole is at 1 over Cp times Ri parallel Rf. Okay. Of course, we won't know where that is for a general value of Cp, but if that happens to be here, okay, if the additional pole happens to be here, you will get ringing, and the closer in it is, the more ringing you will get, and it will go towards instability. Okay. So this is a problem, and this is a very frequently used circuit also. So what are all the things that you would do to make it better? Huh? What are all the things you can do to make it better? Okay, yeah, so first before we start fixing the problem, we should see if we can reduce the magnitude of the problem. Okay, so you should minimize CP. Whenever you design something, you should minimize CP in the first place. Okay, now CP consists of the input capacitance of the op amp. Once you choose an op amp, you can't help it. Okay, that is fixed. An important part of it is you have a metal track here. Okay, so these are all things that come only when you start building stuff. That's why I asked if anyone had built it. The metal capacitance, the metal will have some capacitance to ground plane. If you see how PCBs are made, there are tracks on one side and maybe ground plane on the other side, or some tracks close by and so on. So all of that will also add capacitance. So that you absolutely have to minimize. Okay. The 741 op amp looks like this. Okay. It's in an 8-pin package. This is what it looks like. I think this is minus and this is plus. Now, if you want to make a circuit, the same circuit that I showed earlier, you can do a few things. First, you can draw a track. Let me maybe show a track with this. I can connect RF here and I can connect RI here. Okay, or instead of putting RF here, I could connect it here. Which one would you choose? Does it make a difference? Huh? The area of this copper landing must be the smallest, right? If you want the smallest capacitance. So if you get an opportunity to lay out an op amp, this is what you should use. And similarly, even in an IC, when you do layout, this is the thing to do, right? You have to absolutely minimize the capacitance from the inverting node to ground, because it's going to just introduce extra phase shift and take you towards instability. Okay, so you have to first of all minimize the problem that you have before you start fixing it. And in very high speed circuits, what is done is you have multiple layers of copper. Let's say just take two layers. This is the top and this is the bottom. Okay, so you usually have a solid ground plane, that is the bottom is completely a copper layer, unbroken copper layer, so that you get a good ground plane. Now, if you want a good performance from this type of amplifier, and if you are having trouble with frequency response, what you do is you cut out the copper underneath this. Okay, on the top layer you have this node, okay, whatever this node is. On the bottom layer, and if you have multiple layers of PCB, on all the layers under this, you cut out the copper. Okay, so that you absolutely minimize the capacitance. So these are all the things you have to do. So of course, as far as the schematic is concerned, it doesn't matter where you put this. It's assumed that this whole thing is one node, this whole thing is another node, and so on. But in practice, the area on the inverting node must be made really small. Okay, that's the only one you get good performance from the amplifiers. Okay, let's say we do all this. Then what is the next thing? You still have some ringing. What are all the things you can do? You can reduce both RF and RI. That's the suggestion. Will that work? You reduce both RF and RI, let's say by a factor of 2. What happens? Input impedance is decreased, but let's first stick with stability. What happens to stability? Will it improve? Will it not change it? There is some difference between this and the photodiode. In case of the photodiode, the diode is giving you some fixed current. Okay. If you want a certain gain, you have to use a certain absolute value of RF. Whereas in this case, the gain is dependent only on the ratio between the two. So you can reduce both RF and RI, the pole will move out and you will have better stability. Okay, so that is one of the things you can do. What's the disadvantage with this? The input impedance is reduced. Okay, so that's a disadvantage. Whatever is driving this will have to drive more current if you reduce the value of RI. Okay, so that is one of the things. So let's say we don't want to do this, or we have gone as far as we can. Okay, we don't want to reduce the impedances further. What are all the other things we can do? So you connect the capacitance here. All the other techniques that we discussed will work. Okay. So the first thing is to minimize CP. So that means small landing area or no adjacent metal area. So this is what I meant by cutting off the copper underneath this. And then reduce RI, RF in the same proportion. The disadvantages, okay, then you can have a compensating capacitance across RF, and similarly you can also have a resistance from this point to ground. Okay, so that will reduce the loop gain, increase the secondary pole frequency, and it will improve stability. But as before, the disadvantage is that it will introduce noise. Okay, it is largely similar to transimpedance amplifier. One crucial difference that there the photodiode is giving you some current. You have to amplify that. So the absolute value of RF is fixed. Whereas in this case, the input current you can get can also be multiplied by reducing the value of RI. Of course, this is at the expense of loading the previous stage more heavily. Okay. The other two problems were quite simple. The point in the second problem was that if you use a MOS transistor as a resistor, you use a much smaller area. So it may be sometimes advantageous to use a MOS transistor. The disadvantage, of course, is the nonlinearity of the MOS transistor. The third problem talked about realizing capacitors in different ways. Again, if you use a MOS transistor as a capacitor, you can realize a given capacitance in a very small area, but at the expense of nonlinearity. Now, if you have metal-metal capacitors, they will be linear, but the density is smaller. You can somewhat increase the density by using sandwiched metal layers instead of just using two. Transistors as capacitors, you get very high density. If you use only two metal layers, you get some low density, and if you use multiple metal layers, you get a higher density, but not as high as the MOS capacitor. Okay. So one thing I had asked you to calculate was, you have two plates or maybe a number of plates. Okay. The capacitance between these two is something. The design value was what? 3 picofarads, right? So any capacitor you make will also have this extra riding on it, isn't it? So let's say you make this on an IC, okay, and you put a compensation capacitor. I mean, you put a zero adding capacitor like this. Let's say this is that capacitor. How will you connect it here? So this should be A and this should be B. Okay. If you do the other way around, this will again add to your problems. Okay. So although a capacitor by itself is a symmetrical device, in this case from one side you get an extra capacitor. You should make sure that that extra is driven from the output. Okay. Because the op-amp output has a relatively low impedance, it doesn't matter. But if you make it the other way around, if the parasitic appears on this side, then you all had some parasitic capacitance, you wanted to compensate that, but now you have increased your parasitic capacitance. Okay. So that's something you have to be careful about in general, not only in this circuit, which way you connect it. The capacitance is between A and B, but from A you also have an extra parasitic capacitance. Okay. So one last thing. So let's say we had the photodiode with some capacitance CD. Okay. Now I don't want to use any other thing, right? Anything else. I don't want to use anything like this, and I will adjust the value of RF so that I get the maximally flat response. What was the bandwidth in this case? See, when you are given a photodiode, you are basically given CD. You are asked to get a certain gain, RF. Okay. So now you can choose any op-amp that you want, right? So how will you choose the op-amp? So your RF is fixed because you are asked to realize a certain amount of gain. Your CD is fixed because you are given a certain photodiode. Okay, you can choose any op amp you want and try to maximize the bandwidth. How will you choose it? And I don't want to use this particular technique, the one with the 0. The assignment asks for a different thing. It asks you to calculate RF, but that gave you some relationship, right? You can use the same relationship here. How will you choose omega u given CD and RF? Where was the parasitic pole in relation to omega u? Let's forget the additional pole of the op amp. Let's say it's an ideal integrator. Given RF and CD, the pole will be at 1 over RF CD. Okay? And omega u will be half of this. Okay, this will give you Butterworth response. So what is the bandwidth you will get from a circuit like this? Omega u root 2, which is basically 1 over square root 2 RF CD. So basically the op amp is useless, right? You can't really do anything with the op amp here. You can't choose a faster op amp and get better results. Once you are given RF and CD, that's it. This is the bandwidth you are going to get. You just have to adjust the op amp bandwidth accordingly. Op amp unity gain frequency accordingly. That's all. Okay. So that's why this circuit is, this not using anything is such a poor technique. You have no control over anything. You can't increase the bandwidth even if you want to. If I connect this CF, what happens? I will choose some value of CF for maximum, maximally flat, etc., etc. Now again, is there some benefit of using an op amp with a higher bandwidth? What is the bandwidth in this case? 1 over root 2 into RF CD plus CF. Was that the bandwidth? Yeah. The thing is, can you choose a faster op amp and can get better? Anyway, think about it. Okay. So in this case, it's clear. Is it clear to everyone that you can't do better? So in this case, that's what we did, right? CD and RF are given to you, and then we find that omega u is not even in the picture. So you find out if it's in the picture there. Okay. So I spent a lot of time on this because this is of great practical importance. Even those of you not specializing in analog will probably come across this if you are working with transducers or some optical networks or something like that. Okay. And it's a general treatment of feedback networks. So if you haven't understood it, please go spend some more time on it, maybe re-simulate it with different conditions and see what happens. Okay. And also there were other solutions that were proposed. You can try that as well in simulation. Once you have the bench set up, it should be very easy to change things and try it out.